Welcome, everyone. This new talk is titled Web Extraction with LLMs, presented by Patrick Helena, the engineering manager at Pinterest. He leads the content mining team at Pinterest, which uses MLs to understand the web pages and extract useful information for their users. Please give a warm hand in welcoming Patrick.
All right, thank you, everyone. My name is Patrick. I've been working at Pinterest for the last 3.5 years here in the Toronto office. And this entire time, I've been leading the team that works on understanding web pages. So I'm going to talk today about how we use LLMs, and as a bonus, I'm going to throw in some other models too, and basically go through different ways we can use ML to understand a web page. So first, I'll give a little bit of an intro to Pinterest, to what we do with web scraping. And I'm going to talk about different approaches based on the different modalities of a web page. And then I'm going to talk about something novel that our team's come up with. So let me start off with some audience participation. Has anyone here ever worked on a project with web scraping? I see some hands up. You know, when people are like learning how to program, there's usually some type of little side project you have. You want to get the prices of websites or something like that. And so it's been really cool working in this field on the more of like an industrial scale. And it's interesting because there are so many different approaches. I'll start off by talking a little bit about Pinterest. Hopefully everyone's had a chance to use Pinterest at some point in their life. We've been around for a little while, but basically we help people, give people inspiration to create the life they want to live. So if you're interested in renovating your kitchen, or you're looking for like a new outfit to give a talk or something like that, you can type that into Pinterest and see some different inspirational ideas, these pins. And then you can organize these pins and collect them into boards. We'll understand your taste and start feeding you new pins that might give you more inspiration. So I encourage everyone to download it, check out the app. But that gives you a little bit of a clue as to why web scraping is important for us. So behind most pins, there's a web page. By understanding what's on that web page, we can make our user experience better. So for one, we want to understand the quality of a web page. We don't want to send people to spam web pages. We want to make sure the content on the page matches what's on the pin. We also enrich our user experience by showing people information on the pin that we can find on the website. So in this example pin here, it's a product. We've learned that it's a product by looking at the web page. We have the price and whether it's in stock. That's just a mock pin. If you use Pinterest for real, you'll see even more shopping information. And then finally, aside from showing users explicitly the information we get from a web page, the more information we get about the content, the better we can make recommendations and personalization. So that's why it's so important for us to get all this information from the web page. And I'm going to zoom in a little bit on the shopping use case. This is a field that my team has focused a lot on over the last few years. Here's an example of a product details page. You can see so much information that people use to make purchasing decisions. Things like what category this is it a bestseller, what its final sale price is it in stock? We don't want to waste our bandwidth and people's time by showing them pins which are out of stock. That's a very frustrating experience. So think about how would you train an ML model to get all this different information, the number of reviews, the sizes, the colors. I can tell you it's not exactly a solved problem right now. I can't just grab some open source model and start getting the prices from Adidas and Nike and all that. It's a pretty niche field with a lot of different ways to approach it. And that's, of course, why my team has a job. We're one of the few industry players kind of really focusing on this. So I'll talk through a few different approaches. And these refer to the different modalities, ways that you can represent a web page. One is HTML structure. So if anyone's worked with HTML, you know that you're kind of organizing the content of a page into different sections. This represents a structure. And you can kind of learn which part of the structure has the information that you're interested in. You can also just skip the HTML instruction, all that, and just grab the text, feed it into an NLP model. So ChatGPT, maybe that's everyone's first solution that comes to mind if they were trying to solve this. On the other hand, you can look at the visuals. So if you see what the web page looks like, you can use computer vision techniques. So I'll talk through all three of these. And let's start with the HTML structure. So if people have seen divs and paragraphs and H1s and all that, you're familiar with how HTML can be structured in this different way. it turns into an HTML. When you parse HTML, it turns into this HTML DOM tree. And I have the price node highlighted here. So the goal is to identify the node that has the information that you're interested in. Can we train a model to find these? This is an approach our team has taken very successfully. So you can featurize each node in that graph, and you can use features that come from the structure, so the depth of the node, what type of node it is, information about its ancestors and siblings. You can also use features that come from the content. Is there a $sign in the text of this node? That's a pretty useful piece of information. And our team used a method called wrapper induction. It's a very simple linear model that comes all the way back from 1997. And you're essentially training a regression classifier to go through all the nodes in the DOM tree and figure out which one looks most like the price node, the title node, whatever attribute you're interested in. And we train one model for every single web page and every attribute. That means we have a model for the price on Nike.com, another model for the price on Adidas.com, another model for is it in stock on Wayfair.com. And we have run this in production very successfully. So it's even though it's all the way back from 1997, it's a very accurate model. We have 99% precision on our attributes. And there's a little bit of a caveat here in that we only launch a model if we can see that it's successful. So we have validation to measure each model. Because it's such a simple algorithm, it's very fast to train. You're learning 10 parameters compared to modern large DNN models. It doesn't need very many labels. We get by with less than 10 labels per model. And because it's such a simple algorithm, it's also very fast on the inference side too. So very low compute. And we've successfully scaled this to over 10,000 websites. And a lot of the work has been around building a system to make it easier to scale the training. So detecting when there's an error, making it easy to label and deploy this. And we employ a team of contractors to keep this in production and do the labeling. The downsides are that each website needs its own extractor. The HTML structure doesn't really generalize across web pages. The structure of Nike.com is going to look different than the structure of Adidas.com, even though they have the same attributes. And in fact, it's not even really that robust to changes within a website. If you have training examples of slight variations of a website within a domain, then you can learn about those. But if they make a new deployment overnight, if Levi's makes a new deployment overnight and now they've added some banner about a sale or something like that, it can break your extractor. You have to detect that error, relabel, and then relaunch that model. So it's a lot of maintenance on your existing domains too, which makes it harder to scale. You're spending a lot of resources just keeping your models up and running, which makes it a lot harder to scale even more. So what we want is one model that'll work across all the domains instead of creating one model for every single domain website that we have. Okay, you can also use the structure and apply much more sophisticated techniques. So it's a graphical structure, and you can apply graph neural networks to this. This is something we did a little bit of research on a few years ago. So we've built some prototype models and found that it's promising. You can get some decent accuracy. But overall for us, it wasn't accurate enough to launch into production. It's also very heavyweight compared to these other models. So we didn't actually productionize it, but it just kind of shows you all the different approaches you can take here. You can apply GNNs to solve web parsing. Okay, let's go to the next modality, which is text. So from web pages HTML, you can just grab the text and throw away all the divs and JavaScript and code. And this text I'm showing here, this is a small snippet of the text of that rendered page on the left. You can see there's a price in there, $59.50, but it sure doesn't look like the original text, and you have to kind of really squint at things as a human to get any information out of that. So that shows you how it's a little bit tricky working with text. But if you are going to use text, it's nice to have a language model. So you can apply language models like BERT, Llama, these kind of like open source models that'll tokenize your text and then create embeddings out of them. I'm going to talk about a language model that was created specifically for web pages. This is Markup LM. You can grab this on Hugging Face. Comes out of Microsoft from 2021. When you deal, and it's just like the Roberta architecture, so a BERT architecture. And when you're dealing with transformers, it sees all of the tokens at once. And so one of the components of a transformer model is the positional encoding. With regular tokens in text, the positional encoding is just this is the first token, second token, third token. What's clever about this HTML-based model is that it also has an encoding specifying the location of that text within that web structure. So there's this XPath extractor. The XPath is just a way to note which node in that tree the token exists in. And on top of the normal language model pre-training objectives, like masking out a word and guessing what the word is, it also has some pre-training objectives to make sure it understands the structure of a page. So on this picture that comes from the paper, it has some node relation learnings, like given the two XPaths are these siblings, is one the child of another? So with this model, not only does it understand the semantics, like what these words represent in terms of like human terms, the way that BERT does, it also understands how the tokens are related to each other in the graph of the structure. So that should give us a little bit of a boost. And once you have your language model, and if you want to apply classic NLP techniques, we have two different tasks that we've worked with. One is page classifying. So figuring out, does this page represent a recipe, a product, is it spam? You look at some of the embeddings and feed into a classifier. There's also token-based classification. So which of these tokens, which of the text represents the title? Which of them represents the price? So we've applied this very successfully. It has pretty decent results, and it works across domains. That's great. It's very scalable. In the world of LLMs, the Roberta model is pretty small, 124 million. That's way less than your 7 billion Lambda models. Unfortunately, just like the regular BERT architecture, it has a 512 token limit. In the world of web pages, that will barely get you past the navigation bar in some places. So now you have to employ other techniques like chunking the page and feeding it one at a time. And that kind of adds to the expense. The expense of running this model, not only is it 124 million parameters, much more than our 10 parameter regression model, you have to chunk things and run it multiple times. So we've run this in production on like a limited scale because of its good accuracy and cross-domain scalability. But we've moved away from it now. Now, if you have all this text, another way you can get values is from more generative approaches instead of those classical NLP techniques. If you take the website text, mix it with a prompt, feed it into ChatGPT, it can start outputting the answers you want, kind of like a question and answer type of approach. So in your prompt, you can tell it which answers or what questions you have, and it understands how to interpret the question. If you're training your own model like T5, you can simply train it on the attributes that you want extracted from text. So our team has used off-the-shelf ChatGPT. We have fine-tuned ChatGPT, and we've even trained our own encoder-decoder models based on a T5 architecture. We've seen similar results between the fine-tuned and in-house T5 models, despite T5 models being much, much smaller than ChatGPT. So does this kind of solve everything and that's the end of the presentation? Not quite. We still have jobs. There's a lot of pros to ChatGPT. This is probably the right approach to take it's a very simple approach to start with. You don't need your own GPUs. You can use an API. If you're just using GPT off the shelf, you don't even need to really train it. So it also fixes the larger token limit with ChatGPT. And it gives you decent accuracy. So this is pretty good, and it's cross-domain, scalable. But that accuracy, I have accuracy on both the pros and the cons. It's good accuracy for some applications, but not for ours. We really need closer to that 99% accuracy and precision. We just can't have 1 in 20 models prices being incorrect on Pinterest. And despite the larger token limit, you're still dealing with some web page scaling issues. These web pages are actually pretty large. That slows down your inference. That increases costs. And one issue that you get from text in general is that it's a little bit trickier to get the images and links, right? That's not part of the regular text. So you have to think about, how do I now insert these images in a way that the model will understand? Okay, so let's recap things here. With HTML structure, we find that it doesn't quite generalize across different websites. The structure of Nike doesn't look like the structure of Adidas. With text, it's not really accurate enough for our 99% goals. And there's also issues with large DNNs across the board. They're fairly expensive to run, right? In our use case, we parse over 1 billion web pages a day. And that's what makes some of these approaches too expensive for us to run them on 1 billion a day. You can't really call ChatGPT. Like, think of the bill you're getting from OpenAPI for 1 billion calls a day on these massive chunks of text. Let's look at the last modality. So looking at the visuals of a web page. As humans, this is how we understand information from a web page, right? I have 3 different product details for shoes here. They're from different companies, some different languages, different countries, but you can see a lot of similar patterns between them. As humans, we can instantly see, how do you choose the size? You see a price with a line through it. We know what that means. It's on sale. That's not the final price. That doesn't really get translated to text very well, does it, right? A lot of websites, they're designed to convey information through visual cues, design cues, and those aren't getting picked up in the text. And they technically exist in the HTML, the structure, the CSS, but it's pretty hard to read all that and interpret how it's going to look like and then understand that across different domains. So working with the pure visuals is a way to kind of maybe give us all the information we need and help solve our problem, get the accuracy we want. First, one obvious way to deal with this is you get the screenshot of the page. So grab the CSS, JavaScript, generated screenshot, feed that into a computer vision model. So there's ChatGPT Visual. It can read pictures. You can ask it information. It'll do pretty well. Our team is currently working on benchmarking that, so I don't have exact precision numbers. There's also off-the-shelf OCR-type models that are trained to understand PDFs and other kind of documents with a lot of text in them. And one of those models is Layout LM. That comes from the same team that made Markup LM. So that's one approach, but our team doesn't use that very much for a couple of reasons. First, it's pretty expensive. It's expensive to use the computation to render the page. Are you taking in the JavaScript, CSS, all that, rendering the page? Then you have to create an image out of that, translate all that text and code into pixels. The image takes up a lot of space to move around compared to HTML and pure text. It's also a little bit expensive on the domains themselves, on the websites themselves. You're asking for a lot of information, you're hitting their APIs, you're rendering a live page, so they don't love you asking for millions and millions of these very high data requests on their servers. Another issue is that the images can be missing some data. So we've all seen pop-ups. This isn't like the old days where you can just use a pop-up blocker. Because they don't open up the pop-ups in a new window, they're adding new elements to the page themselves. And it can be hard to distinguish which of these elements are pop-ups and which are part of the page. They obscure information under them. And so you need special code to deal with that. And that makes screenshots kind of tricky to deal with. But you're also missing data in a couple of other ways. So there's an example here of a few different, essentially, tabs of a website. The Material and Care tab is open, so you can see all the text underneath that, but we're not seeing the information below the size and fitting and the shipping returns. So, and the other thing, of course, is links. I can see the image, I can identify what part of the screenshot represents an image. I don't have the URL for that image from the pixels, you've lost that. Now you have to go and map back from that screenshot all the way to the underlying code. So if you think a little bit about what a visual model is doing, you're grabbing the HTML, JavaScript, CSS, rendering that into a screenshot, and now you're handing it off to a model. The model's taking in pixels, applying these low-level features to essentially derive what is the text again, and where are the locations, and then it's going to learn what are the attributes based on that. So this is where our team has a more novel idea. Can we just skip the pixels, keep all the text and layout information, and hand that directly to the model? So this is basically a new way to featureize a web page. We've written code that works with the Chromium rendering engine to just output a set of the relevant text, images, etc., so that it's easier for our models to understand. So here's an example. We have these 2 different text nodes. These represent different nodes in the structure of the HTML. And we're outputting their location, the text inside of the node, and also relevant style information. So we're keeping track of the fact. We know that one of these is striked out. And this is what the web pages actually look like. So on the left, you see the original page. This is what a user is going to see. On the right, you have kind of a reconstructed version of that page. So we took all of those, X, Y, and like raw nodes with their location attributes and just put it all together. And you can see that it's missing some of the details. We don't have the SVG images, and you're missing some borderlines, that type of thing. But in general, you can tell what's going on that reconstructed version of the page. But it's a much more compact representation of the page than the pixels. It has all the underlying links, the image URLs, outbound links. And it takes up a lot less space than the raw pixels as well. It also, because you have all the links and all that, you have more information than what's in the text, and you have all those visual cues that help signify a lot of the information we need. So how do we work with that? We've started creating models. We've really just started on that this year, so it's early days for us. But we're essentially trying to identify which of those nodes represents the attribute that we're interested in. And at this point, our models aren't reading just the list of all the raw attributes themselves, the raw nodes themselves. So we're hand-making features, and we're kind of using some heuristics, like, well, as a human, how can I tell what the title is? Well, maybe it's the largest text on the page. What's the main image? Maybe it's the closest image to the top left corner. The price is probably going to be the price that's closest to the largest image. So we're kind of like, as humans, generating some of these features. And then we're training classifiers on the nodes to figure out, to classify which of these is most likely to be the price, the title, the main image, etc. And we can use very simple models with that. So now we're using complex high fidelity features, a lot of work on the rendering side, but very simple models. So how did that work out? Well, we've got some pretty good results. Right now we're seeing some precision values that are higher than anything we've seen published using our visual page representation extractors. You can see how this accuracy is actually a lot better than the fine-tuned ChatGPT. That's ChatGPT 3.5. 4 was too slow for us. And the other huge advantage here is this is a very simple model, XGBoost models. So these actually can run at a very large scale. They're fast for training and fast for inference. We can do inference on CPUs. And so this helps deal with the scalability. They also work across websites. So we don't have domain-specific models. It helps with scaling up on the number of websites as well. We have applications not just for attribute extraction, but also for classifying the pages. But we haven't solved everything yet. Like I said, we're just starting out early. So here's a couple of things we're working on next. First is scaling up the tasks. I mentioned how we're creating these features by hand at this point. That means every time we want to extract a new model or extract a new attribute, if I want to get the number of reviews, I have to hand make some features, train a new model. Similar to how kind of like DNNs replaced handmade models on pixels before, we're looking to create more of a foundational model that understands some of these patterns on their own instead of our own human intuition figuring out, well, the largest text, that's going to be something useful. That's one area of research for us. The next is scaling the volume. So while the model inference itself is really fast, it's simple XGBoost, we still have the expense of rendering the pages. Unfortunately, we didn't get rid of that. And we can't do that 1 billion times a day. And also, all the merchants are going to complain to us for getting so many resources. So what we want to do is go a little bit back all the way to that first model, but take humans out of the loop. Can we use these very accurate models as teacher models and automatically learn simpler models that'll work on the bare HTML? It's not going to work on every single page. Some web pages just don't have the information you want in the HTML structure. But if we can automate that process, that's going to help us get to that next milestone, order of magnitude in terms of scaling. Okay, that's it for my talk. Like I mentioned, I'm from Pinterest Toronto. So if this sounds interesting to you, we do have some job openings. Take a look at that. Otherwise, feel free to add me on LinkedIn. And I can take some questions now for the next 3 minutes. Thank you. I see a question in the back first. I can repeat the question if you ask. Oh, okay, never mind, I've got a microphone.
Have you tried Llama Index? Because it has like some models for extracting layout, like layout LLM or unstructured IO.
Sorry, what was the question?
It is I wonder just if you try some kind of models, like LLM models, that is related to extracting HTML structures, like Llama Index have layout LM or unstructured IO.
We haven't applied those models yet. So we're looking at layout LM and even ChatGPT visual at this point. But yeah. No, yeah, go ahead.
So like since you mentioned about at the end, doing the vision model, using the vision model to look at a screenshot of a website, and you're doing for this as a production grade, so you kind of like screenshot in thousands of pages. I'm wondering if you can share some insight on how you're gonna bypass like the blocker, like they block you from taking a screenshot and things like that.
Yeah, we get blocked, unfortunately. So that's a little bit more of like a business use case. For the most part, we're giving value back to these domains. They want us to show their products, right? So usually when there's blockages, it's either due to like us, crawling too often. We kind of like partner with them and be like, okay, the QPS rate is too high. We can reduce that. Otherwise, like it's true, using this like visual rendering can kind of trigger some of their more like automated, I guess, security systems. Like they think it's not a human, which is not, but it's treated a bit differently than if you simply ask for the HTML. But what we've seen is it's not non-trivial, but the vast majority of web pages, it's not an issue. So we don't have a way around the block. We don't attempt to get around the blockers or anything like that. So we work more with like business partnerships.
Yeah, so the like the way that you guys approach this is more like you directly talk with the business, and then you try to get them to whitelist you so they can actually. That's
right. Yeah, we have a lot of business partnerships with these merchants and domains because we're sending them so much traffic. So for the larger sites, that's how we try to go about it.
Thank you.
Yeah, go ahead.
Just quickly, what's your coding stack?
Mostly, on the ML side of things, mostly Python. We use some Ray for inference in production, PyTorch, use Hugging Face models where we can. Oh. Passing down the mic.
Yeah, I have a question about the featureization of the recent new ideas you have been presented. So I can understand that the model part you are using XGBoost is very scalable. And how about the featureization part? So what kind of features you have been using, like embeddings or?
Yeah, so exactly those features are extremely simple right now. We've been starting with like simple handmade human heuristics, and our next stage is actually looking at embeddings, or more automated. Like ideally what we want to do is have a model that mixes the text and semantics with this like XY information so that we can learn more about patterns that you see in common websites. So that's basically a next area of research for us, is trying to learn those instead of using heuristics, learn the features. But we've had so much success with the heuristics that it's really more about scaling the tasks as opposed to improving accuracy. And anything else? Okay, well, I see something at the front here. Or okay, sorry, they're going to the back.
While scraping websites, like especially prices, websites have incorporated this JavaScript hidden text field. So like you can see it render, but if you scrape the website or anything, you don't see the field. It's hidden value.
Yeah. That's definitely an issue we've seen, which is a big advantage of using the rendered page. So there are going to be some websites where you won't. Often you'll be able to see like the actual sale price, but you won't be able to see if it was on sale, what the original price was. There are some websites where you can't even see the final sale price without using JavaScript rendering. So yeah, we don't have a way around that aside from this kind of visual-based approach where we're rendering the CSS in JavaScript. So then it's a bit more heavyweight.
So for visual rendering, are you just using like headless browser, something like that?
Yeah, that's right. Basically, Chromium headless browser rendering. We've modified the code to kind of capture the intermediate and output the intermediate steps.
Thank you.
Okay, I'm afraid it looks like we're out of time. Okay, yeah, I'll be over there for any other questions that people have. But thanks a lot for your time, everyone. Enjoy the rest of the conference.